Have you ever wondered if the universe could ever truly be empty? It's a fascinating question that might seem simple at first glance. You might think, sure, just take everything out, and you're left with nothing. But the reality is much more complex. Even if we stripped away all the energy, matter, and radiation, the universe still wouldn't be truly empty. Let's imagine trying to create a true state of nothingness. Even in an empty space devoid of particles and energy, the universe has this persistent habit of generating new forms of energy. It seems the universe just doesn't get our idea of nothing. Surprisingly, even if you remove every bit of energy, you'd still have something left over. The very fabric of space itself. Think about a space where there's no matter, no radiation, and no particles. You'd expect it to be at absolute zero, right? Surprisingly, even in this artificially created emptiness, the universe continues to expand, producing radiation and keeping things from ever being truly empty. This implies that the universe never really achieves a state of nothingness. So, can the universe really come from nothing? It turns out something always seems to exist. Imagine trying to clear a space of all particles, antiparticles, photons, and energy quanta. Even then, you're left with empty space. And within this empty space, quantum fields still exist, following the laws of physics and maintaining their presence even in the absence of detectable matter or energy. Let's go further and imagine being far from any sources of mass or energy. You've cleared the space of external electric, magnetic, and gravitational fields, and no photons or gravitational waves can enter. This kind of nothingness is the closest we can get within our universe. Yet even here, quantum fields persist, and the zero-point energy, a finite, positive, and non-zero value, remains. Interestingly, the universe we see isn't static. It's continuously evolving and expanding. Picture 2 points far apart in space-time. Over time, the distance between them increases, light takes longer to travel between them, and the wavelength of that light stretches out. This ongoing expansion means the universe was hotter in the past and will grow colder in the future. If you could somehow remove all matter, radiation, and every bit of energy, you'd be left with empty space. This space, still expanding and governed by quantum fields, represents the closest physical approximation to nothingness, but true nothingness, devoid of any physical rules or properties, is something that can't exist in our universe. In our universe, even the idea of empty space isn't truly empty. Dark energy, or the zero-point energy of quantum fields, ensures that space always contains some energy. As the universe continues to expand and cool, there will come a time when radiation becomes the dominant component, surpassing all other forms of matter and energy, except for dark energy. Interestingly, before the Hot Big Bang, during a phase known as cosmic inflation, the universe expanded rapidly. This inflationary period explains why the universe appears so uniform and flat today. It also sets the stage for the Big Bang, seeding the universe with the initial imperfections that would eventually form galaxies, stars, and everything we see. Eternal inflation suggests that while inflation ends in certain regions, it continues in others, creating an ever-expanding multiverse. This means that while our observable universe had a beginning, there are countless other regions where inflation continues, possibly forever. The universe we live in isn't just empty space with matter floating around. It's a universe of energy fields, constantly interacting and creating everything we observe. These fields, even at their lowest energy state, exhibit continuous activity due to quantum fluctuations. Brief changes in energy resembling ripples on a pond. Even in their lowest energy state, known as the vacuum state, these fields never truly rest. Pairs of positive and negative particles briefly pop into existence, then annihilate each other, returning their energy to the vacuum. These are known as virtual particles. When the field is excited, it produces elementary particles that interact to form the world we know. Without these fields, particles would drift aimlessly, and the universe would lack the structure and interactions that make it interesting. The interplay of these fields creates everything we observe. For instance, atoms form when quark fields generate quarks, which are held together by gluons to create protons and neutrons. These particles then combine to form atomic nuclei and eventually the elements that make up our world. While the universe is teeming with virtual particles, it doesn't entirely rule out the concept of nothingness. There are still questions about the nature of nothingness before the Big Bang, and why certain elementary particles survived the aftermath of this event. One hypothesis suggests that our entire universe began as a massive fluctuation in the nothingness that preceded it. Ultimately, no matter how vividly we imagine an empty universe, that mental picture doesn't match reality. As long as there is energy within it, even the zero-point energy of the quantum vacuum, there will always be some form of radiation that can't be eliminated. In our universe, true nothingness might only be a concept, an idea that doesn't actually exist. The universe always seems to be full of something, making true nothingness an impossibility. Thank you for joining this exploration of the concept of nothingness in our universe. Remember, even in the vast expanse of space, there is always something filling it, creating the universe we marvel at today. Don't forget to hit that like button, smash subscribe for more jaw-dropping space updates, and join us as we embark on a cosmic journey like never before.